I don't care either way. It's like not that big of a deal. Yeah, you're like, let's finish early. This is great. Okay, so we left off yesterday, Wednesday, talking about some of the alpha and flaviviruses. Some of these viruses that are transmitted by arthropod vectors, so we call them arthropod-borne diseases. Mostly mosquitoes, especially with these viruses. But with both the alpha and the flaviviruses, what we tend to see is a lot of flu-like symptoms, and then the majority of them actually in more severe cases will cause encephalitis. Whereas a couple of the viruses, they kind of jump straight from flu-like to now we're trying to kill you with hepatitis, hemorrhage, and shock. So both dengue and yellow fever can have those really significant secondary complications. So in general, with these two families of viruses, you get cell death through a couple of different mechanisms. One, they take over the protein synthesis, and so they prevent the host mRNA from binding to the ribosome so that it can be translated. They can increase vascular permeability and cell permeability. They can change the ion concentrations in the cell, and they can displace, so they can actually kick it out of the ribosome, not just prevent it from binding. They can actually remove it, and so again you can get cell death. What happens in order for a patient to get one of the arthropod-borne alpha or flaviviruses is they've been bitten by a mosquito. Only female mosquitoes bite, male mosquitoes don't. They usually eat pollen and nectar and stuff, but female mosquitoes require the blood meal to have enough energy and nutrients to lay eggs, to reproduce. So in this case, what would happen is the mosquito would feed from a host who is viremic. The virus is circulating in that host bloodstream. As the female takes what we call the blood meal, the virus gets into the mosquito. Generally, it infects the mosquito intestines, the mosquito midgut, where then the mosquito becomes viremic. It moves into the mosquito or the other arthropod circulation, and eventually moves up into the salivary glands. So it can replicate inside of the salivary glands. As the mosquito moves to the next host from which she's going to take a blood meal, they partially regurgitate as they take a blood meal, so the virus gets in that way. So whenever you're outside, sometimes you'll notice that a mosquito is buzzing you and not biting you. That's almost certainly the male, and he can sense the carbon dioxide and the heat that your body secretes, and he waits for a female to come by because the female's going to come bite you. And so he's like, well, looking for a date. Okay, so that the ones that buzz you are the males, the ones that bite you are the females. Okay. With these viruses, and with every virus we've talked about so far, the disease that you're going to get is determined by the tissue tropism. So what tissues does the virus want to get into? How much virus is there, the concentration of the viral particles. And of course, what's really difficult to measure is what is your individual response going to be? What are your genetics? What is your immune system? And so even if you have two individuals who receive the same amount of the same virus, they might have very, very different responses just because of the difference between every individual. So when patients do experience symptoms, and not all will, you can be infected by some of these viruses and be asymptomatic. You can clear it on your own. They can be very mild, or they could be flu-like symptoms all the way up to things like encephalitis, arthritis, like with the chikungunya, or hemorrhagic disease. So it can be nothing to, it can kill you. It's a pretty wide range of what's going to happen. You never know, roll of the dice. So people who do develop symptoms, again, that initial set of symptoms is most often going to be, for all of these viruses, flu-like illness, fever, chills, headache, backache, right, muscle pain, within 3 to 7 days of infection. And it's, with every viral infection, that's kind of a classic set of symptoms because that's the result of the cytokine response. It's the non-specific viral response. It's just responding to, oh, viral infection, let me do the thing. It doesn't really matter what virus it is. You can get secondary viremia, where the virus can spread to other organs and then cause more severe disease. And that doesn't happen in all people. It doesn't even happen in most people. But it happens in some. And so all of those encephalitis viruses, that secondary viremia is probably going to lead to infection in the brain. So you get encephalitis. With yellow fever or dengue, you're looking more at it can go to the liver, it can go to the endothelial cells. So then you would get the hepatitis. If it goes to the endothelial cells, you can get the hemorrhage and shock. Okay. So hemorrhagic disease and shock come from both viral and immune lysis of the vascular cells. So when the virus infects those endothelial cells lining the blood vessels, yes, you can get the cell death from viral infection, but remember, your most important immune response to viral infection is killing the infected cells. So the viral cells are killing the cells that they're infecting, and your immune cells are killing the virally infected cells. So you're getting that kind of catch-22 of, well, the virus is hurting me and my immune system is hurting me. So this is not so good. You also, because of the cytokines, remember cytokines lead to increased vascular permeability because they want to allow for immune cells to go to infected areas. So you have the increased vascular permeability because of cytokine action. You have endothelial cell death because of viral infection. You have endothelial cell death because of immune cell action. It's just trying to get you like all the different ways. And like we talked about with the reoviruses, when you have the double-stranded RNA intermediate as they're trying to replicate the RNA, that induces an interferon response because our cells don't have, for the most part, double-stranded RNA. So when our cells see it, they recognize it as foreign and mount a response. So it helps to limit viral replication and to stimulate a more robust immune response. As with every infection, our first antibody that will be produced in response to a viral infection is IgM, then IgG. That's what we always see. Antibody can be important because it will neutralize the virus and hopefully keep it from binding to new cells to infect. And what we do sometimes see, especially with the Flaviviruses, so like yellow fever, West Nile, some of the other encephalitis viruses that are related, is a little bit Zika, a little bit of cross-reactivity of the antibodies. It's not perfect, so like having West Nile isn't going to protect you from one of the other Flaviviruses like completely, but it can be a partial type of protection because they have a lot of common antigens. Now, in terms of diagnosing these infections, that also has an implication because there are cross-reactive antigens and your body can make cross-reactive antibodies. It can be difficult using serology to determine which flavivirus it is. Because if the patient has Zika and you do serology, they could test positive for Zika, but they could also test positive for West Nile or yellow fever. So you might use serology as like a primary screening. Yes, this patient has a flavivirus infection. And then you could always try the reverse transcription PCR to identify which particular infection they have. And then the cell-mediated responses are also important, but antibody is one that usually doesn't cause damage to the host. Right? The antibodies don't usually hurt the host cells, but that cell-mediated response can lead to that immunopathogenesis. So I think I already spoiled that one, but the immune response is a double-edged sword. Right? That cell-mediated immune response is great because it gets rid of virally infected cells, but it's not so great because it gets rid of your virally infected cells. And especially if that's happening in the blood vessels, that can lead to hemorrhage. So it's important to, kind of think about those things when you're talking about your patients. So a patient who's immune compromised, Well, that's not good because they're not going to be able to clear the infection, right? So the virus can do a lot of damage. But somebody who's got a really great, robust immune response is also going to have a lot of damage.
Is there ever a point where this type of immunogenicity is advantageous to the virus itself?
The type of what is advantageous?
Like if this immunogenicity, if it's ever is it ever advantageous to the virus itself?
I think it's like that inducing the immunopathogenesis, I think, is more of a side effect. I don't think it necessarily provides an evolutionary benefit. For things like Ebola, to be able to kill cells of the blood vessel and cause hemorrhage allows the virus to spread because that's how it spreads. But in the case of some of these arboviruses, hemorrhage isn't great because it's not nearly as contagious through like direct contact with the blood as something like Ebola is. You really have to have that direct injection of the virus into the bloodstream. And so by killing the host in these cases, it can be maybe not the best evolutionary strategy. So I think the immunopathogenesis in this particular case is just an effect. But it's a good point. It's a good thing to think about when you're thinking about, what are the evolutionary strategies that, as the virus, would allow them to be most effective, and allow them to be able to spread the best way. So like norovirus and rotavirus just get to those extreme numbers in the feces, and they're super, super contagious, and everybody can get those viruses really quickly. So it's a great strategy. But at the same time, you're like, I have diarrhea, I'm probably going to stay home. So maybe you don't spread it very far, right? So it's all those things, those evolutionary trade-offs that viruses and all infectious organisms have to make. But what we tend to see, and this kind of maybe goes along to that point as well, humans are often dead-end hosts for a lot of these alpha and flaviviruses. And by dead-end host, it basically means that not that they might kill people, but that the viral load inside the bloodstream is never really high enough for the disease to be picked up by the next mosquito. So a lot of these arboviruses are not necessarily human to human. And that's why we see things like, 3,000 people picked up Zika or chikungunya in another country and came to the US and nobody else got it. It doesn't mean that that patient wasn't bitten by a mosquito that went and bit another patient. It just means that it's really difficult for that type of transmission to happen because humans don't necessarily get enough virus in the bloodstream to make that efficient. So with a lot of these viruses, another reason that we don't necessarily have them in the US as much is if they're not circulating at high levels in the animal populations. So if we don't have the right animal host, or it's not a high enough number of infected animals, it's not going to persist. And so some of the natural hosts of some of these viruses are shown here. So a lot of them, you get high viremia in birds. So that includes West Nile and some of the other encephalitis viruses, maybe in mice. Dengue and yellow fever are primarily seen in primates in jungle settings. One of the other encephalitis viruses that's transmitted by ticks can be found in sheep, goats, rats, and even in milk. So people who consume sheep or goat milk could get it that way. So again, things like West Nile, the viral load gets high enough that it is a risk during blood transfusions. But again, it's most likely not a risk that if a patient has West Nile and gets bitten by a mosquito, that mosquito can infect another human patient. Usually the mosquito has fed on something like a bird that had a high viral load and then fed on a human, and that's how the human got sick. Humans can be reservoirs for things like yellow fever, dengue, and chikungunya. So more people will have a higher viral load, but for the majority of these viruses, humans just don't get the viremia necessary to be part of the life cycle. So evolutionarily, does it make sense for this virus to infect humans? Maybe not. Maybe not. Maybe it does end up being a pretty poor strategy to get into humans. But I think that trade-off they have is they're very broad host ranges. So if they happen to get in one host that's kind of a dead end, they've got a whole bunch of other hosts that are pretty good. So again, it's that trade-off. Arboviruses, as you probably would expect, occur most frequently when the mosquitoes are out, during warm, moist months. During the winter, for some of these, the virus can be maintained in larvae or eggs. Not all, but most of these viruses, they call it trans-ovarian transmission. The pathogen can be spread from the mother, I guess, mosquito mother, right, the female parent, into the eggs or larvae. Of course, infected reservoir hosts could also maintain the virus during the winter until you have the new population of mosquitoes come out. So this is some of the most recent data for West Nile. I highlighted the Stanislaus County data for 2023, so basically up to like last week of 2023. So the number of total human diseases is 23. 16 of them had neuroinvasive disease, so they developed like encephalitis complications. And then one person was a presumptive test. So what they're showing, these different colors represent different places they found the virus. So this kind of teal or light bluish green, that represents where they've only found the virus in non-humans. So I mentioned on Wednesday that chickens can sometimes be used as sentinels. So they'll maintain monitoring in animals, or they may have found a dead animal and tested it and found West Nile. So it represents that there were no human identifications, but only maybe in a host, or sometimes places actually check the mosquito population as well. You can capture the mosquitoes and screen them for the viruses. This kind of lighter blue, that represents only human infections. They hadn't found it in other animals, or maybe they didn't test for other animals, but they did find it in people. And then dark represents both human and non-human. And so we're up in here with pretty much the rest of the Central Valley. We have it in both humans and in non-humans. And so this is kind of the tracking number of cases since West Nile was found in the US. So we had some big spikes in 2003, 2002. That's 2003, 2004 is when it made it to the West Coast. And then overall incidence during the entire time that we've had West Nile, the highest is in the dark. So you can see in the Midwest. Again, I don't know if you've ever been to the Midwest. They got mosquitoes again that are massive, nasty mosquitoes. And actually Stanislaus County, it's kind of hard to see, but we also have some of the highest incidence of West Nile compared to other parts of the country. And there are a couple of states that don't report county level, they only report state level, so they may not be included as well in this breakdown. Dengue is another one of the infections that we do sometimes see in the US. So this is the data for up to this point, 2023. The states that have the darker, right, they have the highest number of cases. Puerto Rico is also included there. So the number of total dengue cases diagnosed in the United States this year is just over 1,400. 48 jurisdictions, so that would be states and territories. 583 of those cases were locally acquired. So that's a lot. So dengue is one of those I mentioned previously where humans can be a reservoir host. And the locally acquired cases were in Texas and Florida. So again, these are sometimes diseases that you hear about, you're like, oh yeah, these people that go to tropical countries, that's what we worry about. I know Texas wants to be its own country, but I would never call any part of it tropical. Florida's kind of swampy. Not really tropical either. So we have these infections in people, in the mosquitoes, in the US. Maybe not at terribly high levels, but I mean, that's more than like the measles cases this year. So more people got dengue than measles. Again, the majority of patients, if they experience symptoms, it's going to be flu-like illness, but the major complications would be things like encephalitis, which we would see with West Nile, and then any of those other ones that are like blah, blah, encephalitis virus. Eastern equine, Western equine, St. Louis, right? We can see hemorrhagic fever, especially with dengue, because it can target those endothelial cells of the blood vessels. It's estimated that there are annually about 100 million cases of dengue, and that 300,000 deaths result from dengue. So they'll sometimes say that patients have dengue hemorrhagic fever, like when they're experiencing the hemorrhaging, but they also classify it as dengue shock syndrome, and that's, again, where the immune system has basically overreacted and caused too much tissue destruction. And when you have that much hemorrhaging, you end up with shock, the really low blood pressure that can kill you. Yellow fever can also cause liver damage and GI hemorrhages. When it does, that's about a 50% mortality. So in patients who develop those severe complications, it's kind of a coin toss whether or not they'll be able to pull through. You can diagnose via serology, but remember that caveat with the Flaviviruses, you get a lot of cross-reactivity. So the reverse transcription PCR might be kind of your first screening could be the serology. Yes, they have a flavivirus infection. Second, to confirm which infection it is, the reverse transcription PCR. I know that they have started to develop like panels where, because in the doctor game I'm kind of mean and I tell you have to tell me specifically what you're screening for. They sometimes have panels, like they have like an STD panel where they'll screen for all of the sexually transmitted infections or the most common ones with one sample. And I know they're working on kind of like basically a panel where if you suspect a flavivirus, you could just jump right to the reverse transcription PCR, and it can differentiate and let you know which one your patient has. When you have patients who are from more at-risk areas or travel frequently to at-risk areas, sometimes the serology could also catch a past infection. Maybe the patient has yellow fever now, but they had West Nile before, so they're going to have antibodies either way. So that reverse transcription PCR will identify which one is actually causing the infection. Prevention, don't get bit by a mosquito. Easier said than done, right? Same thing with the tick-borne infections, like don't get bit by a tick. That's really it. So of course what we recommend, no standing water, you've probably heard that before. They'll come by and spray, but I know because Fresno has really established that Aedes aegypti, that they'll come around, and if your pool looks kind of funky or you have a funky pond, they'll come in and be like, you have to fix this or we're going to fix it, and then we're going to charge you for it. So if you have that standing water, they'll really come after you. There are some vaccines. There's a vaccine against yellow fever, and there's one against some of the equine encephalitis viruses. They're working on developing a dengue vaccine as well. The yellow fever vaccine was actually developed, one in part because we did have yellow fever in the US, but two, because there's a lot of yellow fever in Panama. And we were very intent on digging a big old canal through Panama. So during the building of the Panama Canal, a lot of people were getting yellow fever and dying, and we really wanted the Panama Canal to be finished. So that pushed some of that vaccine development. Okay, so questions about the alpha or flaviviruses. Okay, so the next group that are kind of in here are the Bunya and Arenaviruses. They're enveloped negative sense strand RNA viruses. They have similar replication. They both can be zoonotic infections, meaning they can come from animals. So even though we've put arenaviruses in here, the ones that we're going to talk about specifically are not transmitted by arthropods, but they kind of fit because they're related. Only really the Bunyaviruses are going to be arboviruses, but the arenaviruses are definitely associated with animal infection. And these can be very serious infections. Some of them are classified as biosafety level 4 because of the hemorrhagic disease they cause, but they can also cause encephalitis. So here are some of them. Again, they're mostly arboviruses in the Bunyaviridae. So you may have heard of some of these. There we go. Crimean Congo hemorrhagic fever. So that's a biosafety level 4. Some encephalitis viruses. Lacrosse is called that because of Wisconsin. Heartland virus, the heartland of the US. Right? So these are viruses that we have that aren't terribly common, but some of them would be considered like emerging infectious diseases. But of course, like this one, Crimean Congo hemorrhagic fever, we don't have that one. So that's always nice. What we are going to talk about today in a little bit more detail are hantaviruses, but specifically the hantavirus we have in the US that's called the sin nombre virus. The hantaviruses, yeah, if you speak Spanish, you probably are like the no-name virus, or the virus without a name. It does, right? Sin nombre. You can say it real scary, but I'll tell you the story of why it's called that in just a minute. Yeah, it's not to be scary. They're not trying to scare you. And they're not trying to make fun of the professors who don't speak Spanish and don't say it the right way. And they're like, sin nombres? That was my Spanish teacher in high school. That's how she talked. Hola, clase. And I'm like, no. It's like, I'm not fluent, but I know that the is silent. Okay. Hantaviruses generally are acquired through inhalation of aerosolized urine from rodents specifically. And it can cause hemorrhage of the lungs and lethal pulmonary disease in the US. And you see deer mice are pretty common here. Okay. You guys can read that on your own. It's very similar to everything else. If we're talking about the arthropod-borne Bunyaviruses, it's just like what we would expect. The mosquito bites an infected host, the mosquito bites a human, and the mosquito lays eggs that are infected. So the new mosquitoes that hatch out in the next season are already infected with the virus and can transmit it right away. We sometimes see that with a handful of our bacterial infections that are vector-borne, like the rickettsia. The tick can lay infected eggs, but things like Borrelia, they don't. So it really depends on the infection, whether or not the arthropod is able to lay eggs that will lead to infected hosts, or infected, offspring that have never had a blood meal before. Okay, so hantavirus, the most recent data I could pull for hantavirus is here from 2021. It's the number of total hantavirus cases that have been confirmed. And you'll see it says confirmed between 1993 and 2021. So 1993 was when hantavirus was first identified in the US. That doesn't mean it wasn't here before. It just means it's the first time that we identified it. And it was found here. I can't remember exactly which state. I want to say it was Arizona, but it was in the Four Corners region. And so originally they called it the Four Corners virus. And pretty much everybody that lived in the Four Corners region was like, no, you can't call it that. We don't want that. There are a lot of Native American reservations in that area, and they rely heavily on tourism. So they're like, please don't tell people that we have some virus that's going to kill them by naming it after our area. And so then it became the no-name virus because they couldn't agree on a different name. So that's why it's the sin nombre virus. But we do have it in, you can see a number of different states. Periodically, there will be cases that come from California. The most recent ones I remember seeing from California were people who were camping in Yosemite. I mean, camping, like glamping? I don't know. They were in like those preformed there's these, I guess, preformed tents. They're not cabins, and they're kind of a double-walled structure. I don't know. I stay at the hotel. I don't camp. And the rodents can get in there and they can, do their thing, right? They live. They're rodents. They build their nests. They eat. They urinate. And so it doesn't look like there's an infestation because when you go into your tent, there are no rodents, but they're in between the walls. And so that can happen.
I'm thinking of a different national park. I was like, was that recent?
It was within the past 10 years. Definitely within the past 10 years. I want to say, I feel like it was after I moved to Fresno. So probably within the past 8 years or so. Yeah. And it happens, I wouldn't say like annually, but with some regularity. We also see it in people who have cabins where they don't live full time. So maybe, like I had a coworker who had a cabin up at Huntington Lake, which is like way north, not way north, it's way up in the Sierra from Fresno. And they only stay there, in the summer. They have to close it up for the winter because they can't drive. Or maybe it's vice versa. You only go visit your cabin in the winter because you want to like sit and sip your hot chocolate or whatever. I don't know. When you're not there, guess who is? Right? The rodents. And so people will come and clean out their cabins. And as they're doing that, that can disrupt any dried urine. It can be aerosolized and inhaled. So that's when we tend to see it more frequently. So year of onset, again, 1993 was when we first identified it, and you see there were a number of cases that were identified. The green represents, well, I guess up here, right? Total number of cases. Green are the people who lived, blue are the people who died, and then these light blue, I don't know, maybe they lost them. It's like unknown outcome. I'm like, it's not like Schrodinger's outcome. Like they're either dead or alive, so I figure they must have lost them. So at some point, they lost them. And then what you see here is county of exposure for hantavirus infection in California. For the most part, there have been 89 total cases diagnosed in California up through 2020. 72, they were able to determine in which county the person had been exposed. And so you see kind of up here, I think this might be Mono County, but this line right here represents the peak of the Sierra. So if you're in Fresno County or any of these counties here, you're like on the west side of the Sierra, and then these you're kind of smushed in between the east of the Sierra and Nevada. So that's where we have a lot. This actually probably could represent right here, Mariposa County. Is the cases like out of Yosemite and places like that?
It was 2012, there were 10 cases.
In 2012, there were 10 cases? Yeah. Out of Yosemite? Yeah. How many died? Does it say? Oh, that's okay. It's not that important. I know, I think a couple people died. And I know they had plague out of Yosemite recently too. Well, within the past like 10 years. I still go. I just don't pet the squirrels, sleep in the hotel, stay on the path. I mean, that's that's good too. You stay home. Keep the rats out. Keep the rodents out. No mosquitoes. See? You're not safe even at home. Oh, so these are some that I like, some headlines that I pulled. Like Lake Tahoe death was linked to hantavirus. Central Oregon woman got it from a cabin. South Reno. So it sounds like, ooh, hantavirus. That's so scary. Good thing we don't have that here. Yeah, we kind of do. So just be careful. Okay, so they can be diagnosed by reverse transcription PCR. Serology can confirm. Again, there is no real treatment with a lot of our viral infections, maybe interferon and nucleoside analogs, but there is no specific, like, you have hantavirus, here's what we're going to do for you. There's nothing really like that. So the idea would be prevention of contact with vectors. So for the Bunyaviruses that are transmitted by mosquitoes or ticks, don't get bitten by a mosquito or a tick. For like Hantavirus in the US, try not to come into contact with aerosolized mouse urine. It's usually my game plan anyway. I know it sounds kind of like obvious, like, yes, I don't want to inhale mouse urine, but you know, if you can avoid it as much as possible, maybe if you do have to clean out a cabin, wear a mask. A good one that can filter out viral particles, of course. Okay, so here's a case of Hantavirus in Virginia. This was a 32-year-old wildlife sciences graduate student, so I guess don't go to graduate school either. At least don't go in wildlife sciences, go in something safe. So the patient presented to the ER in Blacksburg, Virginia, fever, cough, and sore chest. That's what your patients are going to tell you. The student had been trapping, handling, and studying mice during the previous month, and they may not tell you that. They might just come in and be like, I have a fever, I've been coughing, I have like, my chest is sore. So you're the one that has to be like, Hantavirus, right? You have to ask those questions. Neither he nor his colleagues were very bright. They did not wear gloves while handling the mice or their excreta. Like, okay, if you want to, you know, live dangerous and handle the mouse, but like picking up mouse poop and mouse urine and you're not even going to wear gloves? I mean, I'm a microbiologist and I'm like, I'm not going there. No poop. They did not wash before eating. Oh, look, mouse poop. Like, come on, man. And they had numerous mouse bites on their hands. Well, you don't wear gloves, you handle the mice.
They're graduate students?
And the worst thing is I'm assuming they were under the guidance and supervision of a faculty member because we generally are responsible for you. I'm like, no thanks. Okay, so he had a fever and normal lung function. So it basically like he wasn't having like decreased oxygen content in his blood. But a chest x-ray indicated a faint right side pneumonia. So it looks like he's got some pneumonia, but it hasn't necessarily totally interfered with his breathing yet. Then he started vomiting in the ER and they finally admitted him. The pneumonia progressed. He became hypoxic, so now he's not getting enough oxygen. Eventually required intubation and mechanical ventilation. On the next day, he was given something called protein C, which helps to prevent disseminated intravascular coagulation. So remember, sometimes when patients have like a septic infection where they have infection throughout their body, they can get this weird kind of converse set of symptoms where their blood starts clotting. So that's the disseminated intravascular coagulation. It forms like these little microclots. But then because all of the platelets are busy forming these tiny little microclots, they don't stop bleeding anywhere else. So the patient has a ton of blood clots, but they're also bleeding. So they can get hemorrhage from that. The patient continued to fail and died on the third day after hospitalization. Serum specimens contained IgM, IgG, and RNA to hantavirus, and viral antigens were present in the spleen. Although hantavirus received its greatest notoriety with the Sin Nombre outbreak in southwestern US in 1993, it can occur whenever people come into contact with the urine and feces of rodents carrying these viruses. Cases have been reported in 31 of the United States, and that is definitely out of date because that's from 2004. Okay, so, I mean, that's like, I don't even know what you do at that point. Yes.
Did this patient die because like he just had so much contact with the like viral particles, like different ways, like eating and the bites and like, or is it just like, oh, if it was like only one, then he would have still died?
You know, it's hard to say. It could be, so 32, relatively young, right? Probably a nice, robust immune response. But also, like you mentioned, potentially a lot of exposure. And so he could have been exposed to a higher inoculum or to more inoculum than would be expected. And he had a nice, robust immune response. both of which could have contributed. Yeah. I mean, I don't know, like, yeah. Yeah. And he's kind of old for a grad student. The majority of grad students are going to be in their like mid-20s. So I'm thinking this might be a returning student who had maybe a job beforehand, a little bit of life experience. Like, don't play with mice and mice poop, wash your hands. But I'm sure that PI probably felt really bad about the poor training of those students. So the last one I'll talk about just super briefly, you can see some of the Arenaviruses. They're super closely related to the Bunyaviruses, so we do put them together. But the Arenaviruses tend not to be transmitted by arthropods. They're zoonotic infections, but they're so closely related to the Bunyaviruses, we group them together even though they're not arboviruses. Many of these are biosafety level 4, so they are classified in kind of that same way as like the Crimean Congo hemorrhagic fever. The one that most people have heard of is Lassa fever. So they're hemorrhagic fevers. So just like when we see Ebola and Marburg, where you have these infections that are very severe, have a very high mortality rate, we don't have very good preventatives, and we don't really have any real treatment. That's when we're going to get to biosafety level 4. So this is a case of Lassa fever, approximately 10 days after returning from a trip to visit family in Nigeria. A 47-year-old man developed flu-like symptoms. Always flu-like symptoms. He did have a higher than expected fever and maybe a little bit more tiredness. The disease got progressively worse. After 3 days, the patient developed abdominal pain, nausea, vomiting, diarrhea, pharyngitis, like a sore throat, bleeding gums, and began vomiting blood. He then developed shock and died. So these hemorrhagic fevers, they can start out as like, oh man, when you come back from a vacation, sometimes you just feel kind of beat anyway, like the travel and you had fun and you're jet lagged and you're like, well, and you can, be exposed to a bunch of crap on the airplane. There's always that person behind you like, oh my God, why is this person right behind me? So when you don't feel well coming back from a vacation, it's not going to be like, oh, I probably have Lassa or Ebola. And unfortunately, that can be something that happens. Rarely, but if you travel to endemic regions, for any of these infections, it is something to think about. When we start talking about parasites and we talk about malaria, it's something very similar. We don't usually have malaria in the U.S. before this year. It's been a while. But yeah, patients come back all the time like, oh, I don't feel well. And it turns out to be something they never thought of because it's not something that they typically see here. So that's why I do include some of these tropical infections that maybe don't get to huge numbers in the U.S., but they are important because with increased travel, we do see them sometimes. So it's important for you to be aware of them. Yes?
So what would they be transmitted by?
Blood.
Oh.
Yeah. Blood. Animals, like Ebola.
Mm-hmm.
Yeah, these are going to be definitely like zoonotic infections, but then because of the hemorrhaging, they can go person to person that way, like Ebola does. But like Ebola, they have such a high mortality rate that they often like burn themselves out before they can spread. And so that's what they would even do with Ebola. Like, oh, everybody in this village is bleeding out of their eyeballs, so we're just like not going to go there. And it can kind of burn itself out in that smaller area. Any other questions?